Hello, I'm Yuxin Chen from College of Chemistry and Chemical Engineering in Shenmei University in China. I'm now a master student from Professor Paula Zhao's group, which is dedicated in AI-enhanced computational chemistry. In this video, I will talk about how to perform single-point calculations with MLatom. Hope you enjoy this video and provide us feedback if you have any question. If you are not familiar with what MLatom can do and what its capability, you can really check the overview on the top of this MLatom tutorial and also our MLatom 3 paper, which is basically the same. So I will firstly start from this figure I extracted from our MLatom 3 paper, in which all types of methods available are displayed. Here we have various methods in MLatom, including the traditional QM methods. You can check we have the ab initio, DFT, and also some semi-empirical methods. Also, we have the Pretrained-ML models. Now we have the ANI family. And also, if you want to use your own model, we also provide interface to load these models and make the prediction. Finally, we have the most powerful one, the combination of the previous both, the Hybird QM ML methods. You can either use our existing general-purpose AI-QM1 methods, or you can now easily define your own hybrid methods with Python API of MLatom. In this video, I will introduce to you how to make your life easier with MLatom when dealing with all these types of methods. This video will proceed according to this tutorial. We will use the isomerization energy of sugar as the example for the whole tutorial. The geometry file can be downloaded here, and it looks like this. There are two isomers in the given XYZ file, and you can check their geometries. The first one looks like this, and the second one looks like this. The basic idea here is that we will get the single point energies for these two geometries, and then we will calculate their energy difference. Okay, so let's get started. For single point calculations with QM methods, you can really check in detail of this tutorial below. It's here in the simulations category. You can see in MLatom we support various popular QM programs such as Gaussian, PyCF, XTB, etc. The typical input file for the single point calculation should contain this XYZ file, which defines a geometry file, and also you need to define this YES file. This is the file to store the energy. For QM methods, you need to provide the method name here, and also the QM prog, that is the program to perform the calculation. Here we will use the B3lib as the example and use Gaussian to perform the calculation. You can also write the PyCF here. If you want to calculate gradients and Hessian, you can just add two lines behind. This keyword will define the file to store the gradients, and this keyword will define the file to store Hessian. Another thing to mention is that for molecule in MLatom, the default value of charge is 0, and for multiplicity is 1. So you can define charges and multiplicities for these molecules by this. Charges equals to, and these values should be splitted by the commas. Since we only need energy here, we will delete these lines to make things faster. And now we run this command. And it starts calculating. It may take several minutes to finish the calculation. I've already have some output file here. So you can see the energies of these two molecules are listed, and the energy unit in the MLatom is Hatry. The order is the same as that in the input XYZ file. Now we will look at Hybird QM ML methods. For Hybird QM ML method, One of the successful examples is AIQM1. If you are not familiar with AIQM1, you can check our Nature Communication papers. So AIQM1 is a general-purpose method that approaches the accuracy of gold standard Kerbal cluster methods at the cost of semi-empirical methods. In AIQM1, what we actually did is this equation. We used delta learning strategy and correct semi-empirical methods with ML model ensemble. Also, we have the dispersion correction. Beyond this, in MLatom, users can also define their own delta learning model, which will be illustrated in the last part. So for AIQM1, your input file just need to request AIQM1 calculation in the first line, like this. And after running the command MLatom, and within a few seconds, we will get our output file. Here. For each molecule, all the energy components contained in AIQM1 methods are presented, including the ODM2 star energy, and our D4 energy, and the N energy, which is the sum of the NN contribution and the atomic self-energies. The standard deviation of neural network here can be used to judge whether AIQM1 is reliable. We provided in the tutorial here the comparison table. Here you can see AIQM1 is really faster and more accurate than the BiSRLib, so you can really try AIQM1. Okay, next part is about how to perform single-point calculations with user-trained ML models. So, if you have self-trained ML models, you want to use this model to make some predictions, you should provide either ML model type arguments or the ML prog arguments. This is the table for the type of the ML models and the programs available in MLatom. Here we will provide an example for how to use the maze model in MLatom. So for the first line, you need to specify you use ML model. And second line, here is the ML model type. We use maze here, and also our checkpoint file ML model in. We have the maze.d file. Other keywords are as usual. So now we run this command. And after a few seconds, we have our energies in our nest.dat file. If you are a Python programmer, it's good news to you that MLatom now is written in Python, and you can easily import it as a package, like this. If you are not familiar with Python, it's also okay, since Python is easy to read and it's quite intuitive when using Python API of MLatom. Here's the pipeline to perform the calculation. We will first define the method we use, and then we load molecules, we perform calculation, and finally we retrieve the properties from the molecule object. So we start from defining the method. When defining a QM method, you can use MLatom.models.methods class. There are three arguments here which are commonly used: method, program, and unthread. For example, you can define the BiSRLib calculated by Gaussian as this. Here. If we want to change the program to PyCF and use multiple cores, you can specify like this. Program equals to PyCF and threads equals to 18, something like this. For AIQM1, you can directly specify here the method equals to AIQM1. Let me copy-paste this line and change the method to AIQM1. Okay, that's it. If you want to use your own model, here we have different modules listed below. You need to check Python API manual for more details on these modules. For example, If you have a ANI model and you need to define the method to load the model, something like this: mail.model.ani. Then you need to use the model file keyword to specify the checkpoint file. Let's say it's ani.pt. That's it. We finished defining the method. And now we will try to load the molecules. Now we need to load the molecules. MLatom stores information of molecule with atom class, molecule class, and molecular database class. You can load multiple molecules from XYZ file by using from XYZ file function like this. Or you can load only one molecule like this. Now we run this code. Okay, so basically you can see molecular database as a list of molecules and molecule as a list of atom class. You can request the first atom in molecule by index 0, like something like this. Or you see its atom class. And you can, in the same way, you can request the first molecule in molecular database like this. Okay, it's the molecule object and it's the first molecule. You can also check what's inside the molecule class, something like this. Yes, now you can see inside this molecule we have the unique ID, the charge multiplicity, and the list of atoms. If you need to assign charges and multiplicities to molecular database, you can pass a list of values to charges and multiplicities, something like this. And for the molecule, for one molecule, you just need to pass the integer to charge and multiplicity. And thus, we finish loading these molecules and start to perform the calculation. After loading the molecules, we can call predict function in method to perform the calculation. Something like this. Here, we pass the molecular database to the predict function and perform the calculation. If only one molecule is used, you can also pass on the molecule to the predict function. If gradients and Hessian are needed, you can also request these calculations by set calculate energy gradients to true and calculate Hessian to true. After the calculation, energy and Hessian will be stored in molecule object, and the gradients will be stored in atom object. You can request them by using, say, for energy, you can use mol.energy, and for Hessian, you can also use mol.Hessian. For gradients, you need to call mol.get energy gradients here. Worth noting is that molecular database provide function get properties to extract properties from each molecule object. You can extract energy and Hessian from each molecule by using codes like this. And so here is the Hessian. For gradients, you need to use code like this. Okay, so now we get the energy, Hessian, and the gradients from our molecular database and molecule. Finally, we combine these things together. For simplicity, here we will use GFN2XDB, and we load these molecules, we load these isomers, and make the prediction. And after running the calculation, we get the energy for each isomer. Here the unit is Hartree and their energy difference. So we finished the calculation. Now we will look at user-defined hybrid methods. MLatom can combine different models together by use of MLatom.models.modelTree node module, which works similar to tree structure. For more details, you can check Python API tutorial. Here, we will use delta learning model as an example. This ANI model was trained on the differences between full CI and Hartree-Fock energies of H2. That is, we want to correct Hartree-Fock energy to full CI. So we can firstly define the two children nodes. First is the baseline, and then we load this model plus the data correction. Here, you can see there is an operator that operates on the model we defined. Here, each model just performs the prediction task, so this operator should be predict. Now we define the parent node. Something like this. Here, this operator changes to sum, since the operation we will perform on the node, this parent node is summing up the predictions by these two children nodes. Finally, we will use this delta model to predict energy of the molecule. Now we first load the molecule, and then we do the prediction task and we retrieve properties as we have said before. And that's all for the whole procedure.